Hey everyone. So last time we talked about ionic bonding and how it relates to the formation of ionic compounds, and today we're going to get into more specific examples, just kind of elaborating on what we just learned before. More specifically, we're going to get into the transition metals and how exactly the transition metals are accounted for when talking about their ions and their formation in the ionic compounds. So one thing to discuss here is why exactly transition metals form more than one cation. So the reason for that is because of the fact that they really don't have to follow the traditional wanting the noble gas configuration. So the transition metal block, basically the columns 3 through 12 on the periodic table, this rectangle area here, are the transition metals. Many of these elements can form more than one cation, so they can have more than one positive charge. And that's because they don't need to all have the noble gas configuration. Some of these actually prefer to have a full sp and d orbital at that same energy level. Let's take a look at exactly what I mean here with an example with copper. Here's copper's electron configuration. Filling in for the 3d to full up 3d orbital, the copper electron configuration actually has a 4s1 and then a 3d10. That way the 3d orbital is filled up. Now for copper, its nearest noble gases are argon, which means that it would have to have a loss of 11 electrons to get there, or a krypton, or so it would have to gain 7. Both of these are not very practical for copper. So instead, by just losing one electron from the 4s orbital, copper now has a full third energy level. The 3s, 3p, and 3d are all filled up now. So copper will actually prefer to just lose one electron as opposed to try to lose 11 or gain 7 to mimic a noble gas. It'd rather just have that filled up third energy level. So this is what's called a pseudo-noble gas configuration, where it's just emphasizing having a complete energy level filled, including the d orbital filled. So elements that have been seen to do that include silver, gold, cadmium, and mercury. So some of these elements have one, maybe two charges to them, but the transition metals basically prefer to work with their d orbitals as opposed to the traditional s and p, just specifically talking about the noble gas. So for them, it's more about filling up the entire energy level as opposed to just having those 8 valence electrons, which is why some of the transition metals do actually have more than one cation to them. So then if we're talking about the transition metals and compounds, well, we want to know exactly then how can you tell what kind of charge a transition metal is going to have in a compound, and how can you tell them apart? So let's look at the example here with copper, chloride, and both of these. So copper can make two ions, copper plus and copper plus 2. Both of these compounds, if you were to name them traditionally, you'd both call them copper chloride. But then, how exactly do you tell them apart? Well, the answer is you use the anions. So the anions can give you an idea of exactly what kind of charge the copper is going to have. We know that overall, these compounds have to be neutrally charged. So if we don't know what the charge of the copper is, let's just assign it a next value. We do know that chlorine has to have a -1 charge. And we know that the sum of them, of these charges, must equal to 0. So that means in my first example, the charge of copper plus the -1 charge of the chlorine must equal to 0, meaning that the charge of copper has to equal to +1. In the second example, same exact thing. We don't know the charge of the copper, but we know that the chloride anion has a charge of -1. However, in this case, we have two chlorides. So we're going to have two -1 charges. And the sum of these must equal to 0 as well. Meaning here, this copper has a charge of +2. So by using the anion and what we know about the anion charges, we can actually figure out what the charge of the transition metal should be. And we know this because the sum of the positive and negative charge has to be 0 in these compounds. So by using the anions, you can figure out what the charge of the transition metal should be. So then how exactly do you name them? Well, naming these compounds is just like how we've done before, cation name, anion name. However, because of the fact that these transition metal cations can have different charges, we have to include that in their name. And we have to do to include it is just have a Roman numeral. These Roman numerals do not tell you how many of the metal atoms there are, but rather what the charge of them, also known as the oxidation number. So in the first case, we saw that the copper had a +1 charge, meaning that in the name, it's still copper chloride, because copper and chloride are your cation anion, but you add a Roman numeral 1 here. So we call it copper 1 chloride. This 1 tells me the copper has a charge of +1. In the second example, where copper has a charge of +2, again, still cation anion, so copper chloride, but now we use the Roman numeral 2 to distinguish the fact that this copper is different. So this compound with copper having a +2 charge is called copper 2 chloride. So this Roman numeral is the charge of your metal, not the number of metal atoms. You can see that I still have one copper in both cases, but the Roman numeral has changed because the oxidation number or the charge of the metal has changed. So why don't you go ahead and try with these different combinations here. Provide the formula of the ionic compound they make along with the name. And here are those answers.